Welcome back, ladies and gentlemen. Good morning, or good afternoon, or good evening, good night, whenever you're watching the video. We're going to continue by looking at the derivatives of logarithmic functions. We've already looked at exponentials, where I've got a constant to a power. That's actually going to help us today. But we're going to look at logarithms, natural logs, all that other good stuff. And once we know a couple of patterns, once we've memorized a couple of derivatives, everything after that's pretty easy. It's not so bad. So we'll look at the patterns, and then we'll do a bunch of example problems. All right, here we go. So suppose I have the equation y equals log base something, I'm going to call it a, of x. Now a is a constant, and log base a of x. And I want to take the derivative of this. So I want to find y prime of that, or dy dx, the derivative of that. Well, we don't know how to do that yet, but I can do a trick here. I could rewrite this. I could rewrite it in exponential form. In exponential form, this is a to the y equals x. So I haven't taken the derivative. I haven't done anything yet except rewrite it from logarithmic form into exponential form. This I know how to deal with. A to the y, where a is just some sort of number. I know how to do the derivative of that. All right, so now let's find the derivative of this equation. A to the y equals x. So we know this is going to be the derivative with respect to x of a to the y, and the derivative with respect to x of x. Now a to y, the derivative of a to the y is going to be a to the y times the natural log of a. But I'm also going to have the dy dx left over. Dy dx equals the derivative with respect to x of x is dx dx, which is just 1. Now, here's the derivative. This is what I need, dy dx, my y prime. I want to solve for that. So divide both sides by a to the y times the natural log, and I get dy dx is 1 over a to the y natural log of a. And as you can imagine, this a to the y, I mean, that's a bit of a problem. What is that? That's a little bit awkward there. What can I do to this? What is a to the y? I want to replace this. Well, if I look up here, I know that a to the y is x. So I can replace this with x. So the derivative is going to be 1 over x times the natural log of a. In general, we would write that the derivative of log base a of x is 1 over x times the natural log of a. There's our first formula. What about natural log of x? You can imagine that if I'm using natural log of x, something special is going to happen here, because I'm going to be doing, or e to the x rather, and e to the x and natural log of x often undo each other. So let's take a look at the natural log of x, the derivative of natural log. All right, again, let's start with the equation. Y equals the natural log of x. And remember, natural log is just log base e. That's going to be important a little bit later. Let's do the same trick, rewrite. Then I'm going to have e to the power of y equals x. E to the power of y equals x. Now I'm going to differentiate. Take the derivative of the equation, e to the y equals x. And I'm going to have the derivative with respect to x of e to the y, and the derivative with respect to x of x. E to the y, we know this one. The derivative of e to the y is going to be e to the y times natural log of e, which is just going to be 1, times dy dx, equals the derivative of x is 1. Again, if we divide here, I want to solve for dy dx. Dy dx is going to be 1 over e to the y. But what is what is e to the y? Again, I'm going to do that clever substitution here. What is this? we know it's just x. So this is really going to be 1 over x. All right, putting that all together, what is my second rule? The second rule is going to be that the derivative of the natural log of x is 1 over x. All right, let's take a look at some examples. Let's use this now. In my first example, suppose I'm given a function f of x equals the natural log of x squared. Now, natural log of x we know, but x squared. Now, remember, the x squared goes to just the x. It's not natural log of x squared. It's the natural log of x squared. So do you see the chain rule in here? Do you see the outside function and the inside function? If I break it down a little bit, my outside function, my f of u is natural log of u, and the derivative will be 1 over u. My u is some function g of x, which is x squared, and the derivative is 2x. So the outside function is natural log, the derivative is 1 over it, and the inside function is x squared, the derivative is 2x. So putting it all together, I'm going to have 1 over, what's the inside bit? X squared, times the derivative of the inside bit, 2x, which can simplify. The x's are going to cancel, and I'm going to have 2 over x. So my derivative is 2 over x, the derivative of the natural log of x squared. All right, let's take a look at another example. Suppose I have f of x equals the natural log of the cosine of x. Oh, these are getting crazy now, all sorts of crazy stuff going on. Well, again, you might look at this and you might realize that it really isn't that bad. I've got a chain rule going on. My outside function is going to be the natural log of something, the natural log of u. And of course, the derivative we just discovered is 1 over u. The inside function is some g of x is going to be the cosine of x. And the derivative of cosine of x is the negative sine of x. So I've got my outside function and its derivative, my inside function and its derivative. Putting it all together, I'm going to have 1 over u, which is cosine x, times du, which is the negative sine x. Simplifying here becomes a little bit interesting. This is going to be negative the sine of x over cosine x, and we should remember this. This is just the negative of the tangent of x. So my derivative, the derivative of the natural log of the cosine is negative tangent. All right, let's take a look at another one. And here I just want to do a bunch of examples. I'm throwing all sorts of different stuff at you. Suppose I have the following function, x squared times the natural log of x. All right, so what we should recognize here is there's no chain rule, but I definitely have product rule. I've got one function here and another function here. So remember, when we're dealing with product rule, think about the pattern. It's going to be the first times the derivative of the second plus the second times the derivative of the first. I think I can do both of those in my head. So the derivative is going to be the first times the derivative of the second, which is 1 over x, plus the second natural log of x times the derivative of the first, 2x. So this is going to simplify to x plus 2x natural log of x. Hopefully that one wasn't too bad. How about this one? Suppose I have f of x equals log base 2 of x squared plus 1. Suppose we're looking at this function right here. It represents some sort of function doing something, and we want to find the tangent line at some point, the slope of the tangent line. So we need to take the derivative of this. Now, it's not product rule, but do you see the quotient rule? I've got an inside, not quotient, I'm sorry, chain rule. You see the chain rule here. I've got an inside function and an outside function. The outside function is log base a of u. So let's break it down. My outside function, f of u, is log base a of u, where a is 2. I probably should just put the 2 there, make it a little bit simpler. The derivative of the outside function is going to be 1 over u times the natural log of a, which again is that 2. That's going to be 2. My inside function, g of x, is x squared plus 1. The derivative of the inside function is 2x. All right, let's put it all together here. And the derivative of this function is going to be 1 over u, which is x squared plus 1, times the natural log of a, which is 2, natural log of 2, times the derivative of the inside bit, 2x. If I clean this up here a little bit, make it a little look a little bit nicer, I'm going to get f prime of x, the derivative is going to be 2x over the natural log of 2 times x squared plus 1. And I might leave the natural log of 2 over there. I don't want you to think it's the natural log of 2 times that. The natural log of 2 is its own number. And of course we can't cancel the 2's or anything like that. The natural log of 2 is just some number. I have to plug that into my calculator. So to avoid confusion, maybe put parentheses around everything. All right, a little bit harder. Maybe, maybe not, I don't know. Are you getting it? How about if I have y equals 6 to the power of x? All right, so this one doesn't seem like logarithms, but I can use logarithms to help me with this one. If I take the natural log, the variable up here, I can take the variable. Now I've got a constant to a power. I think I already know how to do this one, but let's rewrite it. I'm going to take the natural log of both sides. What's that going to look like? I'm going to have the natural log of y equals the natural log of 6 to the x. Why did I do that? To use the properties here. Natural log of y equals x times the natural log of 6. Natural log of 6, remember, is just some function here. So I've got natural log of y equals x times the natural log of 6. All right, so now let's take the derivative of the natural log of y equals x times the natural log of 6. So I'm going to have the derivative of the natural log of y equals the derivative of x times the natural log of 6. The derivative of the natural log of y is going to be this is remember, natural log of 6 over here is a constant, so I'm going to have 1 over y dy dx equals the natural log of 6. Natural log of 6 is just a constant here. If I want to solve for dy dx, dy dx is y times the natural log of 6. And again, remember, the natural log of 6 is just some sort of number. I don't like having that y there. How can I get rid of this y? Well, remember, y is 6 to the x. So doing substitution here, I get that the derivative is 6 to the x times the natural log of 6. There it is. And I think we could have already done that one a little bit faster in the beginning. All right, so next I'd like to look at a really difficult one, a very awkward one with a lot of stuff going on in it. See if you can follow along on here. This might be one that when you go home to watch just this part again, it's a 15th minute of the video, just to kind of slow it down and take a look at it. Y equals the fourth root of x squared plus 1 over x squared minus 1. Oh yeah, all sorts of horrible, ugly things going on in here. Now, why are we looking at this under our logarithmic differentiation? Well, because I can simplify this by taking the natural log of both sides, and then I can deal with this and I can break it up. So we're going to take the natural log of both sides. So I'm going to have the natural log of y equals the natural log of, and I'm going to write this as an exponent, x squared plus 1 over x squared minus 1 to the 1/4 power. Now this whole taking the natural log, in the next video we're really going to talk about this as its own strategy, and we'll look at another example later, but just kind of brute forcing our way through it this time, and then we'll look at what's really going on, what's the power of what we're doing here. So I want to simplify this. Now that I've got natural log, I can use the properties of logarithms, and I could break this horrible function up. I mean, this is awful. Trying to take the derivative of that is awful. So I'm going to break it up. So I'm going to have the natural log of y equals 1/4 of the natural log of x squared plus 1 over x squared minus 1. And we've got all sorts of quotients and chains and all sorts of stuff going on here. Well, let's break it up. I can use properties of logarithm here. Natural log of y equals 1/4 of the natural log of x squared plus 1 minus 1/4 of the natural log of x squared minus 1. The 1/4 applies to both of them. Quotient rule of logarithms right here. So we're breaking it up. Now I'm going to do the derivative here. I'm going to take the derivative of both sides. So I'm going to take the derivative of the natural log of y equals the derivative of 1/4 times the natural log of x squared plus 1 minus the derivative of, oops, sorry, moving the paper all over the place here, the natural log of x squared minus 1. So I'm taking the derivative now. Now remember, the end goal is I want it to be dy dx equals something. I'm trying to find the derivative of this, dy dx, or y prime. So the last thing, my last line is going to be dy dx equals, or y prime. Remember, same notation here, equals, and then I'm going to have some sort of crazy derivative with only x's over there. If we need to undo a substitution, remember y is equal to that. So anywhere in my final answer that I've got y's, I'm going to put that in there. All right, so let's see what happens next as I do the derivatives. Well, the derivative of the natural log of y is going to be 1 over y times dy dx equals, the derivative here is going to be 1/4, and then I'm going to look at the derivative of what's going on in here. I'm going to have, this is the natural log of x squared plus 1. So I'm going to have, let's see, what's this going to be? 1 over, the derivative of this is going to be 1 over x squared plus 1 over u times the derivative of this times 2x. So derivative of natural log is 1 over, and the chain rule, the derivative of this is 2x, minus, oh, I forgot the 1/4 here, didn't I? Oh, there should be a 1/4 here. 1/4, it's still out there. 1/4 times natural log of u is going to be 1 over this, 1 over x squared minus 1 times the derivative of that, 2x. All right, let's clean things up here a little bit. 1 over y times dy dx equals 1/4 and 2. I'm going to get a 2 in the denominator, x in the top, 2 times x squared plus 1 minus, the same thing's going to happen here, 1 over 2 times x squared minus 1. Solve for dy dx. How do I do that? Multiply both sides by y. If I multiply both sides by y, I get dy dx equals y times x over 2 times x squared plus 1 minus 1 over 2 times x squared minus 1. But again, y. What is y? I can undo the substitution here, and dy dx, here comes my final answer. The y was the fourth root, I'm going to write it as a rational exponent, x squared plus 1 over x squared minus 1 to the 1/4, that's my y, times x over 2 times x squared plus 1 minus, well, that should be an x too, shouldn't it? So it should have an x up here. Oh gosh, did you catch that mistake? Look, this should be an x. I should have an x just like I had it over here. This should be an x. This should be an x over 2 times x squared minus 1. There it is. Pretty ugly, pretty awful. A lot of stuff going on in here. So taking the, and the key was in taking the natural log and then using the natural log derivative. And that is actually a whole strategy in and of itself. And when we get back for part 2 of the lesson, we're going to talk about that. And I'm going to kind of go over the strategy and we'll do some more tough examples. All right, I will talk to you in a few minutes.